All right. Hi, everyone. I'm David Poole. I know a lot of you, so hi. All right. So I'm going to make this very informal. I'm going to talk about what we've done in our book about logic programming and beyond. And then I'm just going to go through some of the slides, some of the things that I think everyone should do and talk about. So it's going to be very informal, um, in the sense that I haven't got a formal presentation done, but I've got slides that'll last me and talks that'll last me for complete slides for a whole course. I could go through if you get bored. So please talk about this. All right. So we wrote a book. Alan Mackworth and I wrote our first book in 1998, which is a long time ago, and that was actually very much a relations first, logic programming first book. And then in 2010, we wrote another book with Cambridge University. That one was with the Oxford University Press. This one's with Cambridge University Press. It was sort of interesting because Cambridge University Press was the only publisher who was prepared to let us have the whole book freely online. Okay, so the whole book is the complete book. All the text is online. And Cambridge were the only people who were prepared to even entertain that idea, and they've had it quite happy about doing this. So the whole book is online, complete text. We also have, well, I can't go back. Yeah. We also have slides for the whole book and resources, including Python implementations of every algorithm in the book, including all logic programming. So we have a Python implementation of logic programming and unification, and all the pseudocode people do in it. There's actually have that in Python. And also lots of prologue code for when we actually get to real logic programming, because my Python is pretty much pseudocode. So all these are supposed to be as close to pseudocode as we can get. All right. All right. So what I want to talk about today was about the logic programming bits. Oh, but let's talk about what's in the book first. So first of all, we talk about agents in the world and agents, and then control, architectures and control, about perception and action and how it all ties together, and you need a belief state. Then we do reasoning and planning with certainty. We do searching, constraints, and here propositional, where we actually do lots of propositional logic, including propositional prologue, propositional logic programming, satisfiability, and all those things. Planning. Then there's all of the things with uncertainty we need: supervised machine learning, neural networks, and deep learning. Reasoning with uncertainty, learning with uncertainty, and causality. Planning and acting. So planning with uncertainty, reinforcement learning, and multi-agent systems. And then we get on, and that's all very propositional. It's all in terms of random variables or features. So we haven't yet talked about, I don't know if you've been to a recent machine learning conference. No one talks about objects. No one talks about things. It's sort of rather surprising to me. But apparently everything's just pixels and words. So that's the only thing that exists in modern machine learning, is pixels and words, as though there's no world, there's no objects, there's no anything. We'll get to that soon. I want to talk about today is this part 5, the individuals and relations. In here it's pretty standard logic programming things. We talk about the predicate calculus, data log, proofs and substitutions, functions and data structures like it normally appear. Applications in natural language. You do an example that's like Chat 80 with questioning and answering on geography, but we do countries of South America. I'm sure Veronica will be pleased. The only thing that's a bit different to the standard way of doing it is some of the things have never made sense to me, of this idea of having a query is false if. So what we do is something that seems much, and the students never understood it. And what we do is something much, what we do is say, so here's an example. Here's a binary search tree for elements of sets, right? You're an element of a set where this is E, you're an element of the left branch and the right branch. And my query is I want an element a set that has 3 in it and a set that has 8 in it. So this is the standard example. But the only thing different here is how I'm going to set this up. Instead of having false if, I'm going to introduce yes. So the idea is that yes, the answer is yes, if 3 is an element of S and 8 is an element of S. So we always have, the arguments to yes are the variables in here. So this is going to be answer extraction. And we go through here and all of a sudden we resolve away the body and we get to this, and this is the answer that we're going to print out. So I don't know how standard this is, but this is much, I think we introduced this in our 1998 book. I can't remember where we got it from. It just seemed to be floating around in the air, I think. And here we do answer extraction. Okay, and then this is the answer. So S equals this is what's printed out by Prolog. And so I think if you're teaching Prolog, this is much more better for is the students understand it, right? But they never understood saying false if and then having horned clauses and refutation and all of that, which is just not needed. All right. All right. Where are we here? All right. Any questions about anything in here? Oh, then we talk about equality. Negation is failure. And every section has a social impact. Every one has a social impact section. How this has impacted society. Most of it's actually quite cynical about the state of the art. So in the neural network, while we talk about stochastic parrots and all the problems that arise with neural networks, here we're going to talk about how Prolog was used for the Watson thing, and also about robot scientist that creates and tests hypotheses. So give examples of impacts about things that are going on. All right. Please ask questions, have a talk. You guys are too quiet. All right. All right. The next, we'll go on then. The next, whoops. Oh yeah. It's interesting, by the way, this one here, Kevin Murphy, who's a bit, is a Google brain, who wrote a very difficult to read but comprehensive book on probabilistic accounts, who actually said he particularly likes the relations late approach, in which the first order logic and relational AI are covered later, after thoroughly covering more basic feature-based methods. So he likes this idea of doing it, even though when we wrote our first book, we were very much into logic programming and thought, well, obviously we're doing this. Obviously, we want all of these things. We want uncertainty, we want planning, we want learning, and we also want first order logic. We also want entities and relations. So that didn't quite work because we had to undo all of the relational things to do everything else. This works quite well, I think, because we can build on top of it.
Okay. Can I ask something, sir?
Please do.
First of all, thank you for coming. I'm Jacinto Davila, the one who wrote the letter for invitation after Veronica and Michael confirmed. Thank you for coming. I'm wondering the basic stuff, well, the basic strategy here, which is that you switch for teaching logic programming with Prolog to teach it with Python.
No.
No?
Sorry.
Some of the code is in Python, right? To teach logic.
All the code that you would all write as pseudocode is now written in Python.
Right.
So when you have the unification code, we have it in Python. So when we have, I'd go to there. So we have So we have so an AI Python. I'll get this. So this is we have it all in this pseudo readable form, which is AI Python, and down here somewhere is what we really have here is this is a document that's written in pseudo literate programming,
Right.
where it intersperses the and so we have a unification algorithm. So instead of having, so here's our unification algorithm. So instead of having pseudocode, which people sort of generally don't like, we mainly write it in this, we give pseudocode in the notes in the book, but then people can actually run it, right? You take the pair, you take, the S is the substitution, these are set of equality things,
Yes.
when we're unifying, and we just do all of the cases there, right? We have test cases, we have a knowledge base, we could actually ask questions in this funny form, but people don't really use this. It's really just so we can have the top-down proof procedure.
Right. That's very useful, of course, because it works.
Yeah.
It runs.
Yes, it works and it runs. And you can do it, and it's sort of the pseudocode you see in other places. But then we quickly jump to using Prolog.
Yeah, but you used to have Prolog code, which is now replaced by Python, isn't true?
We still have Python. We still have Prolog code in here.
Yeah.
In our thing, we still have that.
Yeah, go ahead.
Oh no, I'm just saying that we have. Whoa.
That's the Python code.
Oh, whoops. That's the Python code. Sorry.
So
this other.
So there is still some Prolog in some of the later chapters, and it seemed to me, tell me if I'm wrong about this, but there are some aspects of Prolog that are not yet, ported in effect to Python. That is backwards chaining, and I'm not sure if negation is failure is there or not.
We have negation is failure. It's not the whole Python code is meant to be pseudocode, runnable pseudocode. So we have Python code for all our neural networks. I think it's 10,000 times slower than, or between 1,000 and 10,000 times slower than modern neural network machines. People don't use it seriously in that sense, but people use it because you can read it and understand what's going on.
Yeah, but but specifically about the Prolog features, I'm just wondering about the coverage of Prolog in your Python implementation.
Oh, it's very little. It's just backward chaining, negation is failure, unification. It's basically the pseudocode that would be in a normal book, but it's written in Python. You can run things.
So why do you have any Prolog in the book then?
Because if you really want to run these queries, these if I really want to run some of these programs that do question answering, all the facilities of Prolog are useful.
Okay.
As I understand, I think Adam seems to have or some people seem to have this, what I think is a misunderstanding, and maybe it's my misunderstanding and not theirs, and that is that this book is intended in general to include the teaching of Prolog. So it's basically, the focus is basically teaching Prolog, how it works, what it does, what you can do with it. But in order to teach that, you need to be able to explain what Prolog does. And normally that's done in pseudocode. You give a pseudocode algorithm for backward chaining. You don't execute the pseudocode. You use that as an understanding thing. And as I understand what David's doing and Alan in this book is, they're doing exactly that, except they're decided that their pseudocode will actually be executable. That
Yes.
doesn't mean you want the students to use this code and that's the thing you're teaching. This is just that if they want to more deeply understand the pseudocode, that is the underlying algorithms that drive Prolog, they can actually look at the pseudocode and actually now can run it to understand the pseudocode. But that's not what book is teaching, is my understanding, right? You're sort of assuming that students will have enough of an understanding of Python or will be able to understand it because you're using very simple pseudocodish type things, but you're not teaching Python at all. Is that correct?
Yes, exactly. It's just runnable pseudocode. You can do your examples in there, you can check things out.
Right. So, I mean, having looked a little bit at this, not at the Python section, but at the book, because we used the lectures. We just did this, just finished the semester on this, but none of the lectures really teach Python or Prolog. It's really rather abstract, but there's the definition of definite clauses, for example, right? So that's the connection with logic programming. But all of the labs that you can run and all the experiments, those are written in Python, but a lot of these things are kind of interfaces, right? Where you can input some data or you can run some data and you may get a graphical output. You can do experiments with the code that they've developed. But I don't recall that much of that asks people to do Python programming per se. It's more or less a support environment for doing little experiments. So yeah, I think, David, that your summary there, I hadn't thought of it that way, but now that you say it, it makes more sense that it's the intent is to teach the high-level concepts basically of logic programming, but not teach it with Prolog, but implement some exercises using Python and some little lab-like environments for doing experiments. David, would that be a fair summary?
Well, I recently taught a course on functional logic programming, and it was all, we didn't use the Python code was there if anyone wanted to look at it for the pseudocode, but we just really just taught in Prolog of this, because if you really want to do something, I imagine most of the people who teach this would actually be people who know about Prolog, and we'd be into Prolog and doing things. So it's most people are doing it, I think, with Prolog, not with Python. The Python is just sort of, you can play with this. The AI Python code also contains exercises on how to extend it. So there's some functionality that's missing that you can use in assignments. And that's probably more true in the searching, and because the searching and the constraint satisfaction are actually reasonably efficient. It's the ones where they're like neural networks and Prolog, of where there really is good, well-engineered systems that go much beyond the pseudocode that we expect people not to use.
There is a possibility to have a very nice compromise here. Just one step further from the Python pseudocode is to add a little parser to it and then accept closed syntax. That's what my NatLog system does. It actually has first order engines and a bunch of other things. But the step to go from the pseudocode to actually Prolog in Python is very small. In fact, for a simplified whole closed logic, the syntax and the parser is 80 lines or something like that. So that's why this intermediate possibility to actually run a Prolog in Python, being a Python implementation of Prolog, and then opening all the doors to the neural networks and the complete Python ecosystem is not something to discard just because we are very orthodox on strict Prolog syntax and the usual systems. And the complete language is not important. I think David is absolutely right to focus on the essence of Prolog rather than how cuts and I don't know, IO and other details would work in Prolog, which is not logic programming and not very important to understand uh, the AI part, the symbolic AI part that's conveyed here.
So, in fact, we don't even have a syntax. We don't even have a language of syntax. We just write it in Python constructors, Python classes. So we write a clause, append nil WW, append cons AB to this, where cons is actually a function that returns an atom with the head cons, the body, head tail. So we don't really have a syntax in that sense. There's no parser.
Having a syntax, would be maybe more familiar to people who want to use later Prolog more intensively.
I would, but
from here to horn clause syntax is trivial.
Yeah, but we deliberately, there's lots of sort of filler things we could do that we deliberately didn't do. We're not writing because we don't expect, it's more of an exercise for doing that rather than something else.
Yeah, your Python code is, by the way, very elegant. I saw the yield operation for the interpreter, and there is this natural mapping between the yields in Python and the backtracking in Prolog that you are using. So that elegance actually helps a bit, I think, to use the Python syntax directly. Yeah.
All right.
David, can I ask a question about your natural language grammar? Do you use difference lists or some other
we
way
use
of
difference
representing
lists.
grammars?
So in here, let's find it.
Yeah, it doesn't use DCGs.
No, it doesn't use DCGs. It doesn't introduce a new syntax in there.
I have to be honest, I've done both ways, and I find teaching with DCGs rather difficult. And I'm sorry, with DCGs rather easy, but using difference lists rather difficult. It makes it much more verbose. And getting, telling people, explaining to people how these things parse and reduce after several steps is rather difficult. And you don't see that with DCGs, but that's because it's just syntactic sugar. But it's not clear to me that there's an advantage to just using DCGs. Sorry, there's not an advantage to using difference lists because it.
Oh, hang on.
Yeah,
Where's this?
Yeah, I mean it depends. I mean you have to explain, this the how even in a DCG how the words are being consumed and the rest is being left for the next step and so on.
I
So
mean,
basically whether you use one or the other, I think you end up explaining it anyway.
No, I don't think that's really true. I mean, I think that it depends on what your objective is there. I mean, if you want to teach people about writing a grammar for some fragment of language, you could talk about difference lists maybe once quickly to say behind DCGs, there's this difference list translation. But after that, you can just abandon the whole difference list discussion and, build things up much more complicated that way. If you really had a grammar that was using difference lists, it would look a lot more complicated just to the eyes and to figure out what's going to what then necessary. So if you really wanted to understand the internal mechanics, if it made a difference, because it doesn't, right, then you'd have to do that. But I saw no real advantage to talking about difference lists.
I think this raises what we're discussing here, in my mind, raises a really interesting and important question, and that's sort of the various levels of abstraction that you're thinking about and that you want students to think in. And it's great to teach them the pseudocode for backtracking for a Prolog if you want them to understand Prolog's execution and backtracking. But if you want them to be able to use Prolog's execution and backtracking to, for example, process language, you probably don't want to start and have them thinking about the Python pseudocode. You want to move to a higher level that you can think at that makes sense, this level of abstraction. And the first level one, if you're moving up, you might want to move to is with difference lists, because actually you might want to use a data log with atomic locations in the string. Or you could use difference lists. There, that's logic. But now you can say, okay, we're really just thinking about grammars now. And there's yet a higher level of abstraction of grammars that would be DCGs. And then you can think in that, if you're thinking in that context, then you can do more you can it's easier to know what's important and what's not. It's easier to write grammars if you're not thinking at the backtracking Python pseudocode level, right? So I mean, anyway, so that, and I think that's what I was thinking earlier on here is in this very interesting presentation that David's been giving us, is that in our whole discussion about the pseudocode or the Python, and we got wrapped up in Python and pseudocode, that you're trying, the important thing in my mind about logic programming is the level of abstraction that you can think at, that you can think in terms, of at a much higher level of, the primitives you're dealing with, right? So it's how you, and knowing how the Prolog engine works does not necessarily help a whole lot in knowing how to use Prolog to solve interesting problems, right? And so anyway, I think we need to, I think it's important to teach, and I think that, again, I'm not familiar with this book particularly, but it sounds like it's teaching both levels, but it's spending a lot of time also at how you model problems at a higher level and solve problems with these in the logic thinking world, not in the Python thinking world of procedural execution.
Yes, exactly. Thank you. All right, good. I was going to move on, if I can, if I may. All right, so what I want to do is, whoops, I lost all my position because I changed things. So what I want to do is to talk about the next chapter, about reasoning about knowledge graphs and things. This is what we always have quotes at our start of things. There's a real world with real structure. Program of mind has been trained on vast interaction, contains code that reflects the structure of the world and how to exploit it. Representations of real objects in the world and represents the interaction of real objects. It's a nice quote. It's actually a nice book. Quite old now. We're going to talk about flexible ways to represent relations and knowledge bases made to interoperate. So we'll give an exercise for everyone. How do you represent pen number 5 is red, right? So the obvious way to do it is you write red pen 5. It's easy to ask what's red, and you can't ask what's the color of pen 5. So then we can do, instead of doing that, what else could we do? Well, we could reify red. We could ask the color of pen 5 is red. So now we can ask what's red. It's easy to ask what's the color of pen 5. But what we can't do is ask what is the property of pen 5 that has color red, because it's first order logic. And even if we could ask this, there's lots of things that are true of pen 5. And it seems like there's no disadvantage in doing this to this. Okay. And now we could do it one more time. We could do this reification one more time, and we get pen 5 color red, right? And this is called the triple representation. Turns out this is the only representation we need. We call it the individual property value, the triple representation, all sorts of things, semantic networks, knowledge graphs, and things. So it's the only relation you need. All right. some things seem too simple to ask that, like A is a parcel, right? You could say the prop A is of type parcel, type's a special property, and parcel is a class. To introduce classes pretty quickly. Or you could say prop A parcel is true, and now parcel's a Boolean property, and pass is called the characteristic function of this class. So this happens a lot throughout the book as we have sets and Boolean functions are isomorphic. All right. So we're introducing, types and Boolean functions. And then to represent things like seem too complicated to represent in triples, like Alex gave Chris a book. Well, what we do is we invent, right? We're going to say in prologue, it might be gave Alex, Chris, this particular book. And now to represent that in triples, we can give it a name, we can name, oh, there's a typo here. We could name this this action. So it has a type as a giving action. The agent is Alex. The patient, the person who's is the thing that's being passed is the book, and the recipient is Chris. So you introduce that. And you call this as reifying the action, and then you make it into an individual. So this is how we introduce sort of knowledge graphs, as we're basically reifying things. And it makes it much more flexible if you want to add a date. If you want to add the location, right? You can also add these other things. So it's a very flexible representation of relations in terms of just triples. And then you get to knowledge graphs, which are trendy these days. We'll explain, I'll have time, I'll explain later how. When you only have one relation, you can omit it without loss of information, right? You could do prop. In Prolog, they do the Prolog library, they do call it RDF, or the Resource Description Framework of subject, verb, objects, or just as a triple or a simple sentence, just an individual property value or a subject, verb, object triple, or just as graphically where the entities and value, where the verb is just on the arcs. It's universal. One of the ways of arguing it's universal is you can think of any relational table. You can think about this as just the triple of the row, the column, and the value, right? So this is either the primary key of the row, or it's the reified value. So if you're doing so our students have done databases, they know what primary key is, and you can talk about a booking, a marriage, a flight number, a transaction number. So data systems these days are full of transaction numbers. They're full of reified entities. And it's triple semantic networks as far as entity relationship models, knowledge graphs, concept maps. There's lots of things that are called this. All right. So then the next part is we're going to get to the universal resource identifier's unique name can be used to identify anything. It's just sort of a constant prologue. And this is Tim Berners-Lee naming of things for the semantic, for the World Wide Web. A resource is just anything that can be named. And the modern one we use is the internationalized resource identifier. I always get told that if I use URI because apparently they're old-fashioned. And it's typically got the name of a web address, starting with HTTP or HTTPS, basically because these URLs are unique. And the URI, the internationalized resource identifier, denotes the entity, not the website. They mean the individual. All right. So here's an example of a knowledge graph that's just basically a big set of triples. That's Wikidata. The free collaborative knowledge graph for about 1.25 billion triples describing 100 million entities. I think it's now at 125 million entities described in there. So here's one example. So this is the Christine Sinclair is the soccer player, the football player who scored the most international goals of any football player, man or woman. So she plays for Canada, and she scored more goals than any than Ronaldo or Messi or any of these people in international play. That's why we chose her. She was notable for this. So here's the identifier to use her. This is her identifier. In fact, if I click on this link, I'll open it in Safari, I get to her page about her. But this is actually the description of her page. There are triples about her. Whoops. Okay. Here's another identifier, is schema.name org is a property that gives the name of a subject. And here's another relation, is wikidata.org, prop direct P27 is country of citizenship. And Canada is Q16, is the entity Q16. Christine Sinclair is 267802. So to say Christine Sinclair is a citizen of Canada, you'd write basically the identifier for Christine Sinclair, which is this, but starting with it's this whole thing here. Then the relation is P27 and the entity is Q16. And here is a part of the Wikidata knowledge graph.
Sorry, yes? Are we supposed to be seeing something when you're narrating, or are you doing a screen share or something? Because I'm not.
I am, aren't I?
Yeah, I'm seeing it.
Yes, yeah, we're seeing screen.
Oh, I'm sorry. I don't see that. That's odd. Okay, go ahead. I'm sorry. I'll figure it out.
You may have to disconnect and join again. Might help.
Hang up. You can select which window what you're viewing. I think you can either view the people or the screen.
Okay. No, go ahead. I'll figure that out. Thanks a lot.
All right. And here's an example of the Wikidata knowledge graph. So here's Christine Sinclair. Her name, the name relation is Christine Sinclair. In English, there's her name up here is her name in Korean. She's an instance of human, the country of citizenship of Q16, which is Canada. So now we have reified entities in here. So she turns out she's a member of the Canadian women's soccer team. We have to reify that, and here's the Wikipedia reified entity. Is Q267802. It's actually quite long, the real identifier of that. And then at the start time, she started in 2000. She scored 190 goals and played 319 matches. I think she's just retired last year. She has more than that now. And she's a member of this soccer team, and the country is Q16, and its name is the name of the country is Canada. The name of this one is the Canadian women's national soccer team in English. All right. And you can play with this in Prolog. Let's go to here. So in Prolog, it's actually very easy to do this to query this in Prolog. I'm just going to load this file. Whoops. I'm just using the semantic web library. The semantic web plugin in SWI Prolog, and I'm going to load the Christine Sinclair data set. So if I go this, I believe I can sim web. I can load this file up, and it's going to now download the part of and it loaded 4,226 tuples about her. And we can just ask queries about it. So here are some triples. You can ask it the subject, property, and value. So we can actually ask this. We can ask, here is this entity, it's a type, and there's lots of stuff in here. Lots of metadata in here about this. We can ask for, this is Christine Sinclair, we can ask for her name, so that's following one of those arcs. We can ask for her name, and there it is in Portuguese. There it is in, I don't know, ZH, I think it's Chinese. This is Hong Kong Chinese, and there's lots of, there it is in, so there's lots of different languages. It has her name in it. Okay, so you could ask lots of different, so you could all that graph, we could actually just access directly from, and here's how you'd ask for, if you actually wanted a language in Korean, here's what it is. We could ask for her citizenship, and here I'm asking for, here's the entity, I'm asking for P27 as the citizen, and there's the country is C, and then C, I'm asking what's the name of C. That's what this is doing. And I can ask this. So I can say the entity that she's a citizen of is Q16. The name of this country is Canada. Okay. And we can ask this one here with another statement. So we get this. This one here is asking for, I don't know what this one asking for. I believe this is asking for the name of the country of a team she plays with. So I'm going for the name. I think P54 is plays 14. This is the name of the team. And then I'm going to get the, because it's a reified entity, I have to do 2 steps. So this is the name of the Portland team. So I actually went down this graph here, the member sports team. I went down there as one RDF query. So on this one here, you probably can't read it because it's too small. I went down here. So I asked about the member of sports team and what the name of, and it's the Portland Thorns as the answer it gave me. So it gave me, so it followed down this graph of my graph. So Q261317 is one of the ones it gave me. So it followed this down here. And this is actually the reified statement. This is actually the name of the reified statement that I abbreviated, which is why I abbreviated in my figure. Okay. I can ask for other, there's a different team. This is Gold Pride. There's lots of answers. There's the Canadian Women's National Soccer Team, the Vancouver White. Here's the Portland Thorns Football Club. Okay, so I can do this. I can go through in Prolog, I can ask everything about Wikidata. Students like this because it sort of has, it's much less, it's much more, you can actually find out real things. You can find out every song that Taylor Swift's recorded. There's just so much in Wikidata. It's quite an amazing resource. And it's also interesting because these knowledge graphs are big in machine learning too. There's a lot of part of machine learning that's trendy now on knowledge graphs. So the students like doing this. All right. So we have this, so you can actually go, this is knowledge graphs. So knowledge graphs is just a really simple way to do, going via first order logic and just extending relations. It's a really nice way to introduce it, and it makes much more sense than, because most of the things you read, they get really complicated. RDF has all this really complicated syntaxy things. So the RDF is this language of triples. It has all this really complicated, instead of, you worry about there's so many details in there about how to get things right. The other thing, part of our slides is we have queries. Is there a clicker questions, all of this? So if I'm on Zoom, I'd ask people to give a choice. If I'm in class, we used to have clickers, but now I just get people to raise their finger saying 1, 2, 3, or 4, right? Here's a triple. What's the reason to use this constant name? And I believe the answer is it has a standard meaning and everyone has that constant means the same thing, right? And what's not a reason to use this constant. So we have lots of quickers in here. This Wikidata has lots of weird examples of weird entities. One of the entities is her albums in chronological order. This is Taylor Swift's albums in chronological order. Is an entity in Wikidata. Another one is this folklore album is a particular album of Taylor Swift's. Apparently, it's and if you open it up in Wikidata, you find that it has lots of this data, and it talks about it's part of the albums in chronological order. It has a title, and all of this data we can actually access through Prolog programmatically. So you can actually find lots of interesting different things. Chamber pop apparently is one of the things. There's music. Listening is an entity. A few other things to note in here that we talk about is one of the challenges of doing, there's lots of the data sets around, particularly the machine learning literature. People who do knowledge graphs who don't know what they're doing could publish ones that are now standard for testing knowledge machine learning, and they do silly ways of converting to triples. Often people just project onto pairs. For example, Air Canada flies from New York to Vancouver. Air Canada flies from Vancouver to Los Angeles. And if you convert to triples, you would say, well, Air Canada flies from New York and Air Canada flies to Los Angeles. However, what you've lost here is that Air Canada does not fly from New York to Los Angeles. This information about actual flights is lost. There's lots of people who do very dumb things about converting into triples. And then we talk about the semantic web things, because if you actually want to look at what's Prolog is downloading, it actually ends up this very horrible XML thing. It's readable, but only just. RDF in the language of the semantic web is just the language of triples. So Wikidata will feed it all back to you in RDF. And OWL is some primitive properties. OWL is this web ontology language that we sort of give an introduction to, but it's sort of too complicated and weird for anyone to actually use, as far as I can tell. The other thing that's interesting is a triple store. One of the things that the semantic web library offers you is a triple store. It allows for arbitrary queries. The triple store is interesting because you can store triples. If you're storing a relational database, you need to know what you're indexing on. What's your key? In Prolog, you typically index on the first argument of a relation. However, what we can do with a triple, one of the advantages of triples is that we can ask all sorts of different things. We can ask the subject, give me the verb and the object. The subject and the verb, give me the object. Or give me, is this subject, verb, object true? Or give me all subject, verb, objects true. And if you think about this, there's either the subject is given, or it's constant, or it's a verb, or it's a variable. The verb is either constant or a variable. It turns out you need 8 indexes. So the triple stores just have 8 indexes. Can implement everything with, because everything is indexed now in a triple store. So SWI, their triple store can address 250 million triples. Wikidata has big, you actually can't download it. You can download little bits of it. It's 1.25 billion triples. There are bigger ones. DBpedia is about 15 billion triples. 3.6 terabytes of data. And apparently Google's knowledge graph contains 500 billion facts. So the table that Google gives you when you ask a query is actually derived from something called Freebase, which is a big knowledge graph that's that I think stopped at about 2014. Google bought it and donated all the contents to Wikidata. and it kept building it. And so look at a web page in Google, it actually gives you a table of facts about them, and that's actually part of the this knowledge graph. Now it started to give natural languagey things, but the knowledge graph is much more reliable than is much more reliable than the text, because the text makes up stuff. All right, and we actually have in our Python program actually has a really efficient implementation of a triple store. It just uses all, and it integrates it with the Prolog. So it's actually pretty trivial to write a triple store. So that's how we introduce knowledge graphs. Is basically a way to write. Is a way to write. Is a way to write relations. And then so any questions about that?
So very interesting, of course, and it's great to see these resources. So one challenge is, say you want to say that Christine can only be a citizen of one country. So that I suspect is harder to express, these constraints.
That's what Al lets you do.
Sorry.
Al lets you.
Okay, so you can do that in
Al. That's what Al lets us do. So Al is this language of. So RDF lets you state subclass, class and subclass, and property and subproperty. Al lets you have all these other constraints, like Christine Sinclair, as it can only be the. Interestingly, Wikidata does not use any constraints. There are none of those in Wikidata. The Wikidata does not use anything that's saying restrictions on this.
Right. And I think that's part of the problem, where some of this knowledge is not in Wikidata or DBpedia and all these tools, that you can be citizen of only one country normally, and so on and so forth. The exception.
That's a bad example, but
yeah, I mean, it's normally, again, it's possible, yes, but you get the right.
I think there are lots of, yeah, I know, yes.
So you don't even have key constraints. You don't even have key constraints in the Wikidata.
There's not.
Interesting.
I believe, I don't think there are domain constraints. Basically, it's this enormous thing it's written by.
Just data facts.
Yes.
Pure
facts.
Data
facts. That's all it is.
Any set of facts.
It's all.
But yeah, exactly.
You can edit it. You can edit it. It's editable by people like Wikipedia. But the fact that lots of people come and edit things and change things means that it eventually goes back to it.
So if we want to express, common sense knowledge of the world around Wikipedia, then, a lot more stuff has to be added.
This is just a knowledge graph. It's just a set of facts.
Right. It's very useful. Yes.
There's no common sense here. There's no sense here. It's just the facts.
Data facts. Yes.
Yes. Data. That's right. So the next part of what we do is talk about that. That's a segue to where we're going here. So we have.
Excuse me, can I ask another
Please
question? What are these 8 indexes? This I didn't get.
Each subset of the 3.
Each subset of the 3. There's one index for given a subject and a predicate, return the set of all objects. There's one given all the subject, give all the verb object pairs that are associated with it.
Okay.
So every time you enter a triple, it enters into 8 different indexes.
Okay.
And now it's really fast indexing into each of the. So no matter what you ask, there's a fast index into it.
Okay, great. Thank you.
That's what a triple store gives you. So people sell with triple stores. That's all it gives you. It's just 8 indexes. It's sort of a bit misleading in the sense that if you actually want to do joins, which you need to all the time, they're not really indexed.
Right. The problem is you need primary indexes, and you can't have primary indexes on unless you. I guess you can copy the data. So if you have 8 copies of the data, then you could get more in all the different orders.
So hang on, wait a minute. Now, all we did in our Python implementation, which is actually really fast, was for each of them we just inserted it into in a dictionary with 8 different keys.
Yeah, no, I'm talking about going to disk. I mean databases.
Oh yeah, yes.
If it doesn't fit in memory, then you have to be in disk. And if it's on disk, you need a primary index because you want all of the tuples you're getting together in one block, right?
Yes. The people who sell
if you can put it all in memory, then it's not so. Then there isn't really a
right.
Adjacency location problem.
That's why people actually sell triple stores, because if you just want one in memory one, it's trivial to write. If you want it on disk, it's actually difficult. So that's why when you buy a triple store, that's what you get. Exactly. But I believe you store it 8 times.
I think it depends on the particular implementation this triple store gives you. I think there are various ones.
I'm sure there are. There's lots of, but in general,
I'm not an expert.
neither am I, but particularly not in the disk ones. But that's what the triple store buys you these indexes into each of these. There are 8 indexes. You need to do them, and that's one of the advantages of triples, is that because normally there's exponentially many. If you want to index on every possible query in your thing, instead of just the first word the first argument in Prolog, you actually need every subset of them. So they're exponentially many in the arguments.
If you have try indexing, you can get away with fewer, but that's you still need exponentially many, I believe. I mean, I think you'd only need 5 at most, maybe 4, if you have try indexing on the, you need them in 3 or you need them in.
Oh, I don't know.
Anyway, it doesn't matter. Your points are well taken.
Question related to the competition that large language models give you. You can kind of get with limitations related to occasional hallucination. Everything back in English from a query, and you do not have the ugly syntax of HTTP and all that heavy syntax that Prolog could in theory eliminate if you have a scoping construct. Everything that's redundant could be probably cleaned up with a pre-processing step. But nevertheless, the big competitor is now querying the same thing using natural language and getting a natural language answer back, which is very focused. What do you think about how well this resists competition, or what would be the still important pluses that this approach has to what's now the most obvious way to do those queries with a strong LLM, of course. That's a super good indexer, in fact, in this parametric memory.
It depends on your cost-benefit analysis. How bad is it to get a wrong answer? If you don't really care what's given, then they're fine, right? So if you really want to be careful about, the best example I think is in programming. Programmers use large language models to sort of say, draw me a user interface, and it sort of works. But if you really want to use it, you have to read what's given back and double check it all, right? Because it makes up stuff. It's trying to predict the next word that some random person. So it's trying to predict, given the language model learns probably the next word given all of the context and the previously stated word. That's what it actually learns. And then it samples from that distribution. So generative AI just means sampling from a distribution. And so it predicts the probability that someone who would have said the previous words would say the next. And and it's not trained on lots of facts. It doesn't know about facts. It doesn't know what's true or not. It just tries to predict what someone would say. And if you don't really care about what the answer is, if it just seems plausible and you want to say that, then it's fine. But if you actually care what the answer is, then that's a different matter.
I suspect that for this kind of factual knowledge, which is widely known, it might actually be right. The amount of hallucination may be a lot less. It'll be an interesting experiment to conduct. For example, Christine Sinclair information, I suspect if we ask, every triple probably can be correctly reported by an LLM, I suspect.
I believe it's also learned from these triples.
Oh, yeah, of course. Right.
But there's not something about each of us, right? There's very little about each of us. I don't know if either of us are entities in Wikipedia. We're not celebrities enough.
Yeah, no, very interesting.
Okay, we're
at the top of the hour. Do we want to continue? Stop, or maybe
up to David, I guess.
I'm going for a few more minutes.
Okay, please. Yeah.
Let's just give an overview of the rest of what we did then. I'm lost in my. All right. So that's what so in the knowledge graphs and ontologies thing, we actually talk about ontologies, subclass, so classes and properties. We talk about natural kind. Here's a class hierarchy in Wikidata of the Brazil national football team, and the women's national is a type of National Association football team. The Canadian women's national soccer team is a subclass, is a type of Women's National Association football team, which are all subclasses. So Wikidata does include all this subclass information, which is okay. And we give sort of the logic programming definition of what a subclass means. Okay, and we talk about the domain and range of properties, and properties are functional. That's actually useful later on. These are actually, it's interesting, Wikidata doesn't have domains and ranges or functional, doesn't state this. The date of birth is functional, as people have only one date of birth. Right, so it doesn't have all of these things. So we talk about all these things, the notionship of classes, how to define classes, going back to Aristotle. So we talk about all of these, about how classes and subclasses, how it doesn't, how things like, people get very confused with things like Java because things only have one superclass, where we try and dispel those myths. Like a quadrilateral is that we define a rectangle and a rhombus and a square. So a square is both a rectangle and a rhombus. It's not more directly one of them, it's both of them. And all right, and then we talk about ontologies and knowledge sharing. We actually talk about why we want to do as ontology so we can share data, and finding out what someone else's notation means, but remembering what our own notation means. Right, so given a symbol, determine what it means, or given a concept in someone's head, determine what symbol to use. This is a really hard problem. What symbol should I actually use for something that's in my head? And this is what ontologies are promised to do. So we're going to determine if a concept's been defined. If it has been defined, what symbol to be used. And if it's not already defined, what are related symbols? That's what an ontology thing, that's unfortunately not what they actually do. They're much dumber than that. And we actually talk about we actually give the parts of OWL. So here's the classes of OWL. There's some really weird things in here. I wouldn't teach these. They're just things for people to remember. They're pretty unusable as far as I can tell. and we give some examples. All right. So we talk about those things, and the next chapter is, whoops. Oh, whoops, I'm lost here. The next chapter is about relational learning and probabilistic reasoning. Here's a good quote from Steven Pinker. The mind is a neural computer fitted by natural selection with combinatorial algorithms for causal and probabilistic reasoning about plants, animals, objects, and people. And about how you want to use probabilities. This is all about now learning relations. We're basically going to learn knowledge graphs and other relations from data. And previous editions actually included inductive logic programming, but now everyone does probabilistic predictions. We argue in this book that if you want to make a prediction, you should never believe someone who gives you a definitive prediction. If someone tells you you will not be run over tomorrow, do not believe them. If someone tells you you will be run over tomorrow, do not believe them, right? But a useful prediction gives you, if you do this, here's the probability you'll be run over. So now we're only doing the probabilistic ones in here. And so we then talk about all ways of doing this, about relations and features and random variables. One of the slides, whoops, that's not what I want to do. Whoops. Maybe it's this one. Oh, I've lost it. I have my favorite slide. I can't find it now. Oh, here. So what's the answer to this? So if you, what's the real world made of? Is it made of features of random variables? Is it made of words, pixels, and phonemes? Is it made of entities and events like plants, people, diseases, lectures, or university course? Or is it a real world? Nearly all my students have done statistics courses and machine learning courses. And if you go to those, you believe the world's made of A and B. However, if you actually ask them what the world's made of, they'll tell you it's made of C. It's made of entities. It's made of things. The world is made of things. And it's shocking, I think, about how machine learning is not talking about things. It's not talking about events, objects, relationships, and things. It's talking about words, phonemes, and pixels. All the foundations are talking about features and random variables, if you read any of the books. So we're trying to get people to think about learning in terms of this, and that's what the last chapter's about. That chapter's about.
I thought it was made of a big quantum wave.
It is. That's a thing.
But what you have are abstractions. All of these are abstractions of some.
Oh, of course. Yeah.
I actually think D might be the right answer here.
Oh, yeah. Actually, it's interesting. Half the students pick C and half of them pick D.
Wow.
Very few of them pick A or B. Even those who've been indoctrinated with, and they'll say, oh, yeah. Anyway, the other part of the book is there's a social issues in every chapter, and there's a social issues chapter at the end. At the second last chapter is a chapter on social issues. We talk about all of these social issues of AI and misinformation and the environment and all the potential. So it's not just negative, but it's positive as well. So it's trying to balance out these things about the potential of being able to optimize better. Anyway, I'll finish up here. I think that's all I wanted to.
Thank you very much,
Yeah,
David.
thank you very much.
Very good. Thank you.
Yeah.
Informative talk.
Yeah, thank you.
So I might actually use knowledge graphs the way you have it in your book in the course I teach when I teach it next time, which will be next spring.
Yeah, it's sort of fun. Actually, my course that I gave was a functional logic programming course. They had projects. A lot of them actually mixed up the knowledge graph, the natural language interface prologue part with the knowledge graph. So you actually could ask questions about, I don't know what they ask questions about, all sorts of things. You can actually ask about any Taylor Swift album or anything like that, any pop culture things. It's all in there.
Yeah, and then I guess one could download part of it and then, add additional knowledge and then, build something smarter using logic programming.
Yeah, one could. It's a bit overwhelming. You actually can't download very much.
I mean,
I can.
but few concepts, around something. Yeah.
Yeah, that's right. So that's what I did there. I could ask, questions about people, things that I'm interested or I might want to do. Right, because it's funny. It's pretty complete for. And one of the other problems with learning is that the data isn't missing it. Most people assume learning is missing at random. It's not missing at random. It's pretty complete for all the Taylor Swift fans have got in, the Justin Bieber fans have got in and put all the facts about Justin Bieber and Taylor Swift you could think of. But for most other things, it's pretty sparse. But it actually is pretty complete. It's pretty. People edit it, and it's like Wikidata, like Wikipedia. It's the crowds. If you start putting in nonsense, though, it's pretty quickly gets rid of, particularly for popular topics. I don't think it had facts about Donald Trump anymore because everyone keeps because no one agrees on any of them. It's just the factual ones. So you probably can't. There's lots of things you can't edit.
Related to that, are you also covering the, let's say, less factual aspects of that logic programming can, or logic in general can cover, modalities, epistemic logic, beliefs, all those expressions that are not in this, factual ontology, but which are very important and which are available to logic tools?
Yeah, we don't do any of those. We had to limit it to 900 pages, and that was difficult.
And that's what I was saying, Paul, that, one could add all that, after the fact, download part of the knowledge base and then add all this, knowledge, extra knowledge, and then, do some more interesting projects, again, using logic programming itself.
Okay, any more questions? Well, again, thank you very much, David. And in 2 weeks, we'll have Alejandro. Hope to see you all. And David, if you want to join any other of our talks, just let me know and I'll add you to the list.
I want you to just add me to the list.
I'm sorry?
Just add me to the list that I can.
Great, Laura.
And I'll cover if I want to. And
perfect.
Depends where I am. All right.
Perfect.
All right.
Well,
awesome. Yes. Yeah. Wonderful talk. Thank
Bye.
you.
Thanks all.
Thank you very much.
Yeah.
Bye-bye.
Bye.
See you.